Hi there, I'm Alejandra, Android Developer Relations Engineer.
Hi everyone, I'm Manuel Vivo, same team, same title. Welcome to this workshop where we're going to go through state in Jetpack Compose Code Lab. This Code Lab is a new one. We have revamped the previous version to offer a more comprehensive learning experience. It covers all the concepts you need to learn about how to work with state in Compose. Why, you might be wondering? Well, state is really important for any app, as that is what gets displayed on the screen and brings value to your users.
I'm going to be sharing my screen with the Colab text, Android Studio, and the emulator, so you can easily follow along as we solve it. We do advise that you try to solve it yourself as we code along, or at a later stage.
Yeah, you can find the code lab by either searching for state in Jetpack Compose or following the short link shown on the screen below. Okay, so this is the code lab we are going to work through today. We will cover how to think about state and events in Compose, the mechanism Compose uses to track state changes and update the UI accordingly with APIs such as mutable state of, and finally, how you can use your view models in a Compose app.
So we're going to be building a wellness app. This app will have two sections. In the top section, we're going to have a water counter, so you can keep track of the amount of glasses of water that you take throughout the day. And below, we're going to create a list of wellness tasks, like take a 50-minute walk or read your favorite book. You'll be able to check and uncheck each task to mark them as completed, or delete them if you don't want to do them, so you can clear them from the list. Now we're ready to begin writing our app, so let's start from the top. What do we mean when we say state?
State in an app is any value that can change over time. This very broad definition includes everything from a room database to a variable in a class. State determines what is shown in the UI at any particular time. For example, the most recent messages received in a chat app or the scroll position in a list of items. In the wellness app, state is the number of glasses of water the person drinks, the list of tasks, and whether or not they've been completed. Let's see how Compose uses state to display information on the screen.
Awesome, so let's go to Android Studio now. And I've created a project in Compose from the Android Studio templates, and you can find tips to do this in the step 2 of the code lab. So let's jump into step 3 then. I've also implemented the first basic composable functions we need to set up in this step. So we can see what we have so far. So first up, we have our main activity, what we are calling the wellness screen. So if we go to the wellness screen, we have a composable function representing the only screen of our app. Right now, it has the water counter, but as we progress with the code lab, we will have more functionality here. And then we jump straight into the water counter, which is a composable function with a variable count initialized to 0, the most basic example of state. And we pass it into the text composable function, so we can display the amount of glasses of water. And that's our full path. So now if we open our emulator, we have our app running like so. What we see is the output UI, the result of Compose, taking your state, transforming it into the UI that you see displayed on the screen after running all your composable functions. But as we said before, state is any value that can change over time. And our state here is static, it's hard-coded to 0. So what we want is to be able to change our state and modify the count and add more glasses of water. So how can we do this?
With events. In Android apps, state is updated in response to events. Events are inputs generated from outside or inside our application. For example, the user interacting with a button on the screen or the app receiving the response of a network request. In all Android apps, there is a UI update loop that goes like, state is displayed on the screen. If an event happens, the event handler changes the state, and now the UI displays the new state on the screen, and so on. This cycle repeats indefinitely.
So let's introduce a way for the user to generate an event to be able to update the state, which means, in our case, change count. So if you follow the tips of the code lab to implement the changes for this section, you'll end up with a code snippet that looks like this. Let's take a look at what we added. So we added a button. that receives an onClick lambda function to execute when the button is clicked. We want to increase count in 1, like so. We also added a label to the button so it says add 1 instead of just having an empty button. And to align these two elements vertically on the screen, we just surround them both with a column. And then we just add some padding here and there so things look nicer on the screen. You can just run the app to see how this looks like. In the meantime, to learn more about column, row, modifiers, and all things layout related, you can follow the basic layout in Compose collab right after this one. So we all go to the emulator and we run the app. We have a button, we click it, and we see that nothing happens. Why is that?
Let's see. A bit of theory is coming, so please, people watching this, bear with me and pay attention that this is important. We know that Compose transforms data into UI by calling composable functions. The output of this is what we call the composition. That is, the description of the UI built by Compose when it executes composables. Now, if a state change happens, Compose re-executes the affected composable functions with the new state, creating an updated UI. And this is called recomposition. But in order for Compose to recompose and update the UI accordingly, Compose needs to know what state to track. Compose has a special state tracking system in place that schedules recompositions for any composables that read a particular state. This allows Compose to be granular and just recompose those composable functions that need to change, not the whole UI. The small caveat here is that you need to use Compose's state APIs. As you saw, using regular variables in a composable function don't cause recompositions. So which ones are those APIs, Ale?
So the API we want to use, so Compose knows which state it needs to track, in our case count, is mutable state. We can create mutable state with factory method mutable state of, like this. Let's just add the relevant imports, mutable state class and mutable state of factory method. And let's jump into the definition of mutable state to take a look at what's going on. What this class does is wrap your state of type T inside a value parameter that is observed by Compose, this parameter value. So now what you can do is read your state by accessing this value. So if we go to a what encounter now, we're going to see that we have a compilation error, and we can do what we just said. Instead of accessing count directly, we can just now call a value. In the same fashion, instead of printing count like so, we can print a count.value. We format the class a little bit, and we run the app now. And because we're now using Compose API mutable state, Compose is tracking changes to count, meaning whenever we press the button and increase count, the composable function recomposes and the UI should show the updated value, right? Well, not yet, because nothing happens. Why is that?
The mechanism is working, it is recomposing, believe me, but the problem is that when the function re-executes, the variable is reinitialized to 0 again. That's why we always see the 0 glasses on the screen. We need a construct that saves the state whenever Compose recomposes this function.
This is where Remember API comes in handy. And we can just wrap your mutable state off with the remember inline composable function like this, add t import like so, run the app, and in the meantime, we can just take a closer look at what's happening. A value calculated by remember is stored in the composition, and the stored value is kept across recompositions. So we go to the app and click our button now, we see that the state is actually working.
Nice. Cool.
Yeah. So usually, remember mutable state of are used together in composable functions, because your logical path would be to update your state and have it survived a recomposition so you can display it properly on the screen.
Talking about syntax now, there are a few ways to deal with the state APIs. Accessing the value property every time, like we are doing now, is one way. Another way, which can be more convenient in this case, is with the by keyword, which uses Kotlin's delegated properties. With by, instead of a val, count should be now a var. This approach makes you avoid accessing value property of the state, so that you can modify the grabbed state directly in the code as if it was the actual value. You can see how the code looks much simpler now. For other syntax options, check out the compose state documentation. Each one has its pros and cons.
So, what have we done so far? We have our state count variable defined as mutable state, so Compose is able to recompose whenever this value changes. And thanks to the remember function, after the function recomposes, your state survives and is displayed properly on the UI.
Nice. I think we can move on to the next section then, state-driven UI. Compose is a declarative UI framework. Instead of removing UI components or changing their visibility when state changes, we describe how the UI is under specific conditions of state. This way, as a result of a recomposition, composables might end up entering or leaving the composition. If a composable function is called during the initial composition or recompositions, we say it is present in the composition. A composable function that is not called is absent from the composition.
So, we'll modify our water count to composable function to show some UI based on our state. Let's say we want to show the text only if count is greater than 0. So we can just add a simple if method like so and move the text inside like this. And now we have it. And next, what we can do is configure our button to be enabled as long as count hasn't reached 10 glasses. We can do this by using the enabled parameter in the composable in the button composable function. So we have on click, we have the enable condition, and last we have the modifier. So you can just format the class a little bit, and that is it. We can run the app now. We're going to use the layout inspector here to take a closer look at what's happening as our state changes and our function recomposes. You can find the layout inspector in two ways, like I just did in the bottom right tab of the IDE, if you haven't done any further customizations of the Android Studio, or you can go to Tools, Layout Inspector, and then you can open it like that. Just make sure to be running your app on a device using API 29 or higher for this test. Let's go to the emulator now, and we have the layout inspector showing the first initial components tree, where we see, if we examine it a little bit, in the bottom, we see our button and a text that happens to be the add one text, as we have it in the screen, like so. So now what we can do is just tap the button. We see that the layout inspector now shows another tree as it refreshed. What we are showing, what the layout inspector is showing now is the same button with the text add one, but something has been added. Now we have the text showing that you've had X amount of glasses of water. So we can see that the tree has dynamically changed. And now let's click the add one button and we'll see that our composable function recomposes, like so. And the button has been disabled, just like we configured before with the enabled parameter. So this is what we mean when we say that UI is declarative in Compose. We define what our UI looks like under certain conditions of state with simple Kotlin logic, like an if condition. And if a component doesn't need to be visible, you just don't add them to the composition. And they are not added to the tree that Compose generates. And when the state changes, the state will drive what elements are present in the final UI. So let's just close the layout inspector and stop it, as we are not going to be using it further, and we're ready to move on to the next step.
Cool. This is actually a very nice and definitely the power of Compose, being able to define your UI declaratively. But not only composables are stored in the composition, also the memory they create using the Remember API, for example. That memory or object stored will be forgotten if your composable function recomposes and the source location where that remember was previously called is not invoked again.
Please make sure to check out step 7 of the Code Lab, where we show a detailed example of that mechanism in action.
Mm-hmm. Cool, back to our app. I was wondering what would happen if you have some glasses of water on the screen and you rotate the device. Can you try?
Sure, let's see. We can add just a couple glasses and then we can rotate the device. And what we see is, okay,
Yeah,
yes.
as I suspected, state hasn't been restored properly. Let's see why that happens.
Great. So let's go to the water counter. And what we have to do now is replace remember with remember savable. And let's give it another try. So why remember savable? Why this API? Well, remember helps you retain state across recomposition. It's not retained across configuration changes. For this, you must use remember savable instead. That will persist your state in a bundle. So now what we do is the same test. We add some couple of glasses of water and we rotate the device and we see that our state is persisted.
Nice. Nice one.
Yeah.
Cool.
So, quick recap. You use remember savable to restore your UI state across recompositions like remember, but also across configuration changes like orientation, like this case, or switching to dark mode, and across activity and process recreation.
Definitely. That's a very handy API to know about on Android for sure. Okay, for the next section, we'll need another theory break, I'm afraid. Are you ready for it? Okay, a composable that contains internal state is a stateful composable. These composables tend to be less reusable and harder to test. Composables that don't hold any state are called stateless composables, which are more reusable and easier to test. An easy way to create a stateless composable is by using state hoisting. State hoisting in Compose is a pattern of moving state to a composable's caller to make a composable stateless. State hoisted in this way has some important benefits. First, it has a single source of truth. It can be shared with multiple composables. It is also interceptable by callers that can decide to ignore or modify the state, and it decouples the state from the composable itself. Ale, what if we provide stateful and stateless versions of that water counter?
Yeah, what we want to do is split the water counter into the stateful and the stateless water counter. So let's just go open the water counter now composable function and think what's the state that we actually want to hoist or extract. And in our case, of course, is count, as we saw before. So the first thing that we want to do actually is just move this state a little bit up like so we can see this clearer outside of the column. So now we can actually draw a line like this that will separate visually where we are defining our state and where we are reading it and writing it. So the refactor could be quite simple in our case. The first thing that we want to do is just select the part that will be stateless and just go and hit refactor function. And let's say that we call this the stateless counter, like so. So let's clean our implementation a little bit here. First, what we want to do probably is add a default modifier for our modifier param. Have our count be the first parameter, like so. And let's clean up count a little bit as it created a duplicated version of it. So let's just use count everywhere, like so. And now, obviously, we cannot mutate count directly here anymore. So what we want to do probably is expose an event, which is what happens when the button is clicked. So let's add a lambda function to do this. Let's call it on increment, like so. And let's pass it down to the button itself, like this. And that is it. That is our stateless counter. So now let's go and create our stateful counter, which will look like this is almost done. Actually, let's just refactor and click rename as a stateful counter. We don't need to, this is a pop-up that asks us to rename the file. We don't need to rename the file, it's fine. We can skip this bit. And we almost had it. The count, state count, is defined just how it was before. And now what we have to do is just call the stateless counter here, passing the count variable like so. The onIncrement will be our lambda function, the behavior when the lambda is called, which is just increase the count by 1, and the modifier will probably be our modifier parameter, like this. And that's the stateful counter also done.
Yeah, I mean, if we look at stateless counter for a second, we can see how it takes state count as a parameter and it exposes an event, onIncrement, as a lambda function. The pattern where state goes down and events go up is called unidirectional data flow, UDF. And state hoisting is how we can implement this pattern in Compose. You can learn more about this in the Compose architecture documentation.
Cool, great, awesome. So now if we run the app after this refactor, you'll notice that everything is working, and we get all the benefits that we mentioned before. So for example, your stateless counter here can now be reused in multiple parts of our app with different count variables, with different state. So if we define a new state variable, say for example, juice count, we can use the same layer, stateless counter. Instead of using our state count, we're gonna call juice count like so. And this is it. This stateless counter layer being able to be reused fully, right? So this is very powerful. Let's just, like, that's example number 1. And on the other hand, the stateful counter, this counter, can provide the same state that we hoisted, count, to multiple composable functions that may need to do something with it. Let's imagine we have another counter composable function, another counter, like so. It receives the same state, and instead of adding 1 to it, it just multiplies it in 2. So it's able to modify it. It's able to modify it as well, which is also very useful. So make sure you check out the code lab if you want to take a closer look at these 2 examples. So in the meantime, I'll just clear this a little bit. And that's it. Now that we've finished with our water counter refactor, it's probably a good time to jump onto the next piece of functionality that we want for our app, which is the list of wellness tasks.
Sure thing. So we are in the work with list step of our code lab already. Let's continue with our wellness app. Let's add the feature that displays a list of wellness tasks on the screen, shall we? As we can see on the design, given a task, you can mark it as completed or remove it from the list. Let's see how this looks.
To have our list, we need to follow a series of steps. Let's take a look actually to the design first. First, the item. We want to implement a composable function like this with a text, a checkbox, and a close button, and both buttons aligned to the end. Remember that all the code that I'm going to be writing here, you can develop yourself following the code lab tips, and then you can check the solution. So we're going to have a composable function that looks like that. I have it already implemented. It's called wellness task item. So let's move it to our main package and close this view. So it will have the checkbox that we were mentioning before with the Boolean state checked to indicate if it's checked or unchecked, and an unchecked change lambda function, which is what happens when the checkbox changes its state. We also have an icon button with a on-click lambda function. So we want to hoist this check state and the events for both buttons to make the function stateless. So we get all the benefits of state hoisting that we saw before. So let's create a stateful version of this composable that owns the checked behavior. So your snippet will look something like this. We define the check state with the APIs that we learned before. Remember, a mutable state of a Boolean in this case. We pass the state down to the stateless wellness task item here. So it's important to notice that this item is every item in the, like every row in the list, and each check state is independent per row. So we pass the unchecked change behavior lambda function so the event can flow up when the checkbox is pressed. And as per the onClose lambda function here, don't worry too much about it. We will implement it in a later step. So next up, what do we have to get our list completed? we need a model class. We have a wellness task. Let's move it to our main package as well. We have this class, which is just a simple data class with an ID and a label representing a task. And what else do we want? We want the actual list that we were mentioning. So let's just have it here and implement it like so. Let's take a closer look. So we have a method that creates fake data to test, in our case, 30 elements of type wellness tasks. And what we also have in the list compose is our list composable function, finally, receiving a list of remembered wellness tasks of this method of fake data. And why is it remembered? So the list survives recompositions when this function recomposes. For instance, if this was a network call, it wouldn't be re-executed again, for instance.
Mm-hmm. And as we don't know how many tasks we'll show in our app, we can use the lazy column API to display the list of tasks on the screen. In it, we can use the items method to specify what content to show. To learn more about lists, check out the list documentation or the Compose layouts workshop.
Sweet. So now the only thing that we're missing in this step is creating the items by calling the stateful wellness task item we just wrote before, like so. So this is our wellness task item, and we pass in the task label of the model that we have. Final step, we call our list into our main screen, the wellness screen. So I want to do here is actually add the wellness task list, like so. And so these both things are properly aligned on the screen. What we can do is just surround it with a widget, in our case, a column. And we can just use the modifier from the parent. So it's inherited throughout the rest of the composable. And that's it. So now we can run the app, and what we should have is our water counter like we had before, and our list of wellness tasks with the checked behavior working. And there we have it.
Cool, that's very nice. But I think we might have an issue still. What happens to the state of the individual items on the list if you scroll down and then back up? For example, let's say you're going to mark the first tasks and then as completed, and then you scroll around a little bit. Are they still checked?
Okay, let's give that a try. So let's say we checked 0, 1, and 2, scroll all the way to the bottom of the list, all the way to the top, and yes, the state, apparently we are losing the state.
Yeah.
Let's take a closer look at which state we're losing, actually. So the state we are losing is this one, check state, in each item. So all we can do is just use our infamous remember savable API here, like so, and we run the app again to see if this fixed the issue. Remember savable is useful not only to make your state survive configuration changes, which is not what's happening here, but also to retain state when your items leave the composition entirely, which is the case of our items when you are scrolling and they are no longer visible. So if we run the app again, we open the emulator and we do the same test as we did before. We check 0, 1, and 2. We scroll all the way to the bottom and all the way to the top. And now we see that our state is properly preserved now, only with a similarly small change and all the power of remember savable.
Cool, this looks amazing. Good job. So yeah, I think that's pretty much it. The only thing left is implementing the onClose button behavior for our items on the list. Removing tasks from the list would mean mutating the list that was static before. Apart from mutating the list, we need to make it observable by Compose, so that Compose recomposes whenever the items on the list change. So that's what this section is about. We are going to see how we can make a list observable by Compose. A list that is observable by Compose is of type snapshot state list, but you don't need to deal with that API directly. You can use an extension function on collections called toMutable state list, Or you can create a brand new list using the mutable state list of API.
Great, so let's start by modifying the wellness screen. And after implementing the tips in this step of the code lab, you're gonna end up with a snippet that looks like this. So what do we have here? What we want is our wellness screen to be the source of truth for our task list, so that the tasks can be used in other parts of the screen, not just our list. So first, what we want to do is move our list of fake data, our fake data method generator. And we define our list like so, to instantiate the list, calling the get wellness tasks. And to create a list that is observable by Compose, we call the toMutableStateList extension function mentioned before. Now our list is observable by Compose, and anytime the list is mutated by adding or removing items, and we're just going to be removing items in our case, this will cause a recomposition of the UI. You could have also written this syntax in another way by using mutable state list of, which is similar to mutable state of API that we used before. And it will look something like this. We can comment this bit of code and show this snippet here. It doesn't matter to add the imports right now. We just want to take a quick look. So we could have done this. One thing to keep in mind though, you should create the mutable state list of and add all initial elements to the list in the same calculation of the remember function. So in one single step, you have your list created with all of the initial values. What you cannot do though is have something like this, in which you first define the list for the remember function and then add all the elements in a different step. Why? Because this will cause that every time this function, composable function recomposes, you'll be incorrectly re-adding, duplicating items to the list, and we don't want to do that. So let's just clean this up a little bit. So now it's a good time to actually jump into wellness task list and address this onClose task lambda function.
Since wellness app is the single source of truth for the list, it means that only this function can modify it. As a best practice, you shouldn't pass mutable state around, as you are going to lose the single source of truth benefits. Therefore, you need to pass the functionality of removing items from the list in a lambda down through the UI tree until it gets to the close icon itself.
Yep, definitely. So now we can go modify the wellness task list. So first thing, we can remove the method that creates fake data, goodbye, and remove the list default as well, like this remember list here, as we've hoisted all of that to the screen level. Let's also rearrange this parameter here to be the first parameter, like so. And then we can add the onClose lambda function parameter to this function and pass it down to the wellness item. The onClose task receives a task we want to delete, like so. So this is now a brand new lambda function. And now what we want to do is just call the wellness task item with an onClose lambda function that will receive our onClose task. And we pass in the task that we have. And that is it. Because it is a good practice to pass composables only what they need, we don't want to pass the entire task model down to the wellness task item, because we have the task hoisted at this level and it's not necessary.
One thing to add at this point is that the items function in lazy column can take a key parameter. By default, Compose tracks items on a list based on their position on the list. If the position of that item changes, Compose needs to recompose all the items shown on the screen. That feels suboptimal when an item just changes its position on the list itself. But we can make Compose track items on the list in a different way by specifying a key. In this case, we want to uniquely identify tasks based on their ID, not on their position.
Sure, let's do that. And that's this is how you write it, by adding the key to the items itself.
Yeah, so in this way, if an item on the list just changes position, Compose can identify that instance in the composition and move it to the right place without having to recompose all the items.
Awesome, great. So that's it for the list composable then. We can jump into the wellness task item and pass in our onClose Lambda function where it needs to be. So we have our task name, we have a modifier as the last parameter, and now we can define an onClose Lambda function. Here is what we were aiming to implement later, so we can just pass it down, and now the stateless wellness task item already receives onClose into the icon button. So everything is connected now. We can run the app, and what should happen now is that both our check state and our delete functionality are working now. So let's just open the emulator and we see exactly this. We see that the check behavior is working, and the removing 1, 2, and 3 is working as well.
Cool. Oh, wow. We've done a lot of things in just a short amount of time. We have a list that is observable by Compose. Each item on the list also holds mutable state for the checked and unchecked status, and that state is also observed by Compose and preserved when items leave the composition or the app goes through a configuration change.
Yeah, that's great. But now that you mentioned configuration changes, I wonder what if we remove some elements of the list and then rotate the device.
Yeah, good point. Let's see what happens.
So now I already removed a couple of items between the 0 and 4th, and if I rotate the device now, what we see is that they are actually back. And there is probably another test that we could do. If we check elements 1, 2, and 3, and say we remove 1 and 2, and now we rotate the device, there. So they are all back. So the state is not restored properly. The check state was restored as if the item was not deleted at all. What we would have wanted to see is the items 1 and 2 fully removed. So remember, Saveable is not going to help us this time to retain all changes to the list, including deletions. We would need a custom saver in this case. And you can read more about this in the documentation and the collab around saving your state for our app. However, another alternative is to use view models as a way to deal with state preservation across configuration changes for the list. So Manu, can you tell us a little bit more about view models?
Yeah, that's one of my favorite topics. And that's exactly what the next state of the Code Lab is about. If you're familiar with view models in Android, you would be very interested in learning how to work with view models in a Compose app. But in a nutshell, view models provide the UI state and access to the business logic that might be located in other layers of the app. Additionally, and the reason why we are mentioning view models here is because they live longer than the composition, which means they survive configuration changes. This makes them a good fit to host UI state, for example, our list of tasks. There is a lot to learn about view models in Compose, so I would recommend reading State in Compose documentation if you want to know more about their role in a Compose app.
So let's migrate the list and the remove behavior over to the view model. Let's start by creating our view model class, and I have it here that we're also gonna put in our main package like so, and we can implement it again following the Code Lab tips. So let's take a closer look at what we are doing here. We have a list defined in the same way as before in a private variable task this time, because we don't want to expose the mutable list from the view model to the exterior so anyone can modify it. Instead, what we want to do is just expose a task variable that it's read-only. And we also moved here the fake data generator method. So now what we have to do is just instantiate this view model in our wellness screen. We can access a view model from any composable by calling the view model function. To do this, this function is in a library that we need to add to our screen, to our app. And I'm just gonna show real quick which one this library is. The library is Lifecycle View Model Compose here. I've already added it and synchronized my project, so we can add it we can use it directly now. So let's jump back into the wellness screen where we can use it. What we're gonna do is just define my view model using this function as a parameter, actually, with a default value. So it can be hoisted if anyone needs to later. We add the relevant import and format the class a little bit, and that is it.
Actually, this is a very common pattern in Compose, actually. If your parameter can potentially benefit from state hoisting, go for it. The caller can always ignore it if they don't need to intercept it. In this case, the view model could be replaced and faked for testing, for example. Also, this view model function returns an existing view model or creates a new one in the given lifecycle scope. It is scoped to the closest view model store owner, which is the activity in this case.
So I'll remove our fake data method because we have it in the view model now. And like so. And what we also want to do is remove the definition of the list because now it's stored by the view model itself. So now let's just delegate all of our state and the behavior that we have in the view model down to the wellness task list, like so. The task will look like this, and we are calling the view model's remove method. And we're done. So now we run the app, and since the state is kept outside of the composition and stored by the view model, mutations to the list survive configuration changes. We can do the same test that we did before by checking 1, 2, and 3, removing 1 and 2 tasks, rotating the device, and now what we see is that the state is properly preserved thanks to the view model.
Cool, it is working. Nice one. Yeah, I think that's pretty much it, right? Are we missing any state that we might want to migrate to the view model as well?
Yes, definitely. We could also migrate the check state over to the view model. So our code is simple, more testable, and all our state managed by the view model. We actually covered this final step in our code lab, so make sure you go there and check it out.
Definitely. Oh, one last thing about view models is that it is a good practice to use them in screen-level composables. You should not be passing view models down to other composable functions. That's going to violate the single source of truth principle, and also you could get scoping issues. You can safely use view models in composables that are close to an activity, fragment, or the destination of a navigation graph. But as I mentioned before, check out our docs if you want to know more about the role of view models in Compose.
Yes, definitely great points there. So that's what we have for you today. Congratulations! We've worked through the state in Jetpack Compose code lab.
Hey, well done! We covered how to think about state and events in Compose, how Compose tracks state changes, and how you can use your view models in a Compose app. But there is so much more that you can do.
We recommend that you take a look at JetNews, our sample Compose app that showcases the best practices that we explained today. Also, check out the final section of this collab for links to documentations, further reads, and APIs.
Thanks for watching this workshop, and please let us know in the comments if you are still with us and whether or not you coded along with us. Thanks, have a nice one. Bye!